Hi, in this video I will introduce refraction and Snell's law. When electromagnetic radiation, and that includes visible light, moves from a vacuum into another medium, a solid, a liquid, or a gas, it slows down. The amount it slows down by is dictated by the refractive index, which is also known as its optical density. This is a property of particular materials, and it can also be affected by the frequency of the light itself. We'll look at that later. The refractive index has the symbol n, and it can be calculated with the equation n equals c over cs, where c is the speed of light in a vacuum, so that's 3 times 10 to the power of 8 meters per second, and cs is the speed of light in whichever medium we're interested in. By definition, the refractive index in a vacuum is 1. Air causes light to only slow down by a tiny amount, so the refractive index for air is 1.000293. So we're going to just use 1. Water has a refractive index of 1.33. So light moves 1.33 times slower in water than it does in air. And this is why we can sometimes be deceived by the position of an object in water, as the light is bending as it moves from the water into the air. Glass has a refractive index of around about 1.5, whereas diamond has a much higher refractive index, about 2.4. This is why it's easy to tell the difference between a diamond and an identically cut piece of glass, because the diamond will sparkle more due to the additional refraction taking place because of this high refractive index. As we know, light slows down when it passes from one medium into another. Let's take a look at the boundary between two materials, air and glass. We're going to shine a beam of light at this point here, going from air with a low refractive index into glass which has a higher refractive index. A dashed line has been drawn perpendicular to the boundary. This is called the normal line, and it is very important. All angles must be measured from this line and never from the boundary itself. If we shine light along the normal line, nothing appears to happen. We can assume that it slowed down when it entered the glass, but we've got no real way of knowing for sure because it's still going far too fast for us to actually measure. So let's rotate the light source round a little bit. Notice that two things are happening. Firstly, we're getting some of the light reflected back. This partial reflection obeys the laws of reflection. In other words, it reflects at the same angle from the normal as the incident ray. But for now, we're more interested in the ray that continues into the block. Notice that it has changed direction and bent towards the normal. If I swap the materials round and have the light going from glass into air, notice that the opposite effect occurs. The light has got faster and bent away from the normal. The relationship between the refractive indices of the two media and the angle through which the light refracts is governed by an equation known as Snell's Law, which says that n1 sine theta 1 is equal to n2 sine theta 2, where n1 is the refractive index of the first material, n2 is the refractive index of the second material, theta 1 is the angle of incidence measured from the normal line to the incident ray, in other words the ray that is going into our boundary, and theta 2 is the angle of refraction measured from the normal line to the refracted ray. Let's calculate the angle of refraction when the angle of incidence, theta 1, is equal to 30 degrees for a ray that's going from air into glass. Well, the refractive index n1 of air is 1, whereas the refractive index for glass is around about 1.5. So we want to find the angle of refraction, theta 2. So first let's rearrange our equation for sine theta 2 and substitute our values in. So 1 multiplied by the sine of 30 degrees divided by 1.5 gives us 0.33, and then if we inverse the sine on 0.33, That gives us 19.5 degrees. So let's check that with our PhET simulation. And yes, we can see that our incident angle of 30 degrees gives us a refracted angle of 19.5 degrees. Let's finish by quickly considering some of the other factors that affect refraction. When light moves from one medium into another, its frequency is unchanged. Since we know that light moving into a higher refractive index slows down, and we know that c equals f lambda, we can deduce that the wavelength must also decrease in proportion to the speed. Although frequency doesn't change when light passes from one medium to another, frequency does affect refraction. The refractive index of a material varies slightly according to the frequency of the radiation. This means that higher frequency blue light will be refracted more than lower frequency red light. This can cause white light to separate into its constituent colours, and is called dispersion. It's the effect that we see in rainbows and prisms.